In this video, we are going to look at the negative binomial regression model in Stata, which is another model besides the Poisson regression that is used to analyze count outcomes. Specifically, we are going to check for the main assumption of a negative binomial regression analysis, and then we interpret the results of our analysis. If you want to know how to carry out steps 2 up to 5, consider watching our previous videos under binary logistic regression analysis in Stata. The principles under each of these steps is essentially the same. The main assumption of a negative binomial regression analysis is actually the assumption of a Poisson distribution, which assumes that the mean is equal to the variance for your outcome variable. And our outcome variable in a negative binomial and also the Poisson regression model is a count outcome. The negative binomial regression is only used if this assumption is violated. It is used when the mean is not equal to the variance, but specifically in a scenario where the variance is greater than the mean, a term called overdispersion. When there is overdispersion in your data, or when the variance is greater than the mean for your count outcome, then the negative binomial model is what you use instead of Poisson model because it corrects for overdispersion. So it is important to check whether the assumption of the Poisson model has been violated before we can proceed to run our negative binomial regression. Otherwise, if the assumption is not violated, then we go back and use the Poisson regression model. So to test for this assumption, we can crudely obtain the summary statistics to compare the mean and variance, or we can test the overdispersion parameter, which comes together with the output of a negative binomial regression, as we shall see shortly. But this overdispersion parameter, it is basically testing the assumption that there is no overdispersion, whereas the alternative is that there is overdispersion. Here is our hypothetical data set that we want to use to demonstrate how to run negative binomial regression. We have our outcome variable, which is the number of times someone visits the doctor. We've called it clinic visits, and it is a count outcome, a requirement for negative binomial regression. We also have 3 independent variables that we want to use to predict how many times someone visits the doctor using negative binomial regression. Before we do that, we have to first test for the assumption of mean being equal to variance. We can only use negative binomial regression when this assumption has been violated. So we shall start by obtaining the descriptive statistics so that we compare the mean and variance through statistics, summaries, tables, then summaries and descriptive statistics, again summary statistics. In this dialog box, we are going to enter our outcome count variable, which is clinic visits, and then we shall request for display additional statistics. Click OK. In this output, we are interested in checking the value for the mean. Here it is 4.06. Comparing it to the value for variance, here we have 14.5. Clearly, the variance is far much bigger than the mean, a term called overdispersion. By crudely comparing the mean and variance, you have an indication that the assumption of Poisson distribution has been violated. We therefore need to go ahead and carry out the statistical test on the dispersion parameter to see whether it is equal to 0 or not. This will be obtained after fitting the negative binomial model through statistics, count outcomes, and then we select negative binomial regression. In this dialog box, we specify our dependent variable, which is clinic visits, and then our independent variables. We have age, and then gender and education, which are categorical variables. We are going to put them through these 3 dots. click on them. Then we leave it as factor variable and main effect. Then we enter them here. Gender, we add to variable list, and also education, we add it to variable list and click OK. Then you will see that there is an I dot before the variable name for the categorical variables, showing Stata that these are categorical variables, and click OK. Here is our output for the negative binomial regression, but before we interpret anything here, we need to look at the likelihood ratio test of alpha equals to 0. This parameter alpha is our dispersion parameter in the negative binomial regression model. And this test is testing whether alpha is equal to 0 or whether the dispersion parameter is equal to 0. We can see that the p-value is less than 0.05, meaning that it is statistically significant. So we reject the null hypothesis that says that the value is equal to 0. In other words, there is over-dispersion. When there is over-dispersion, you go ahead and use the negative binomial regression model. Otherwise, if there was no over-dispersion, or if we had the p-value above 0.05, then it tells us that the mean and the variance is equal. It has fulfilled the assumption for a Poisson distribution. We would go back and use the Poisson regression analysis. So because of this statistically significant p-value, we are going to proceed to fit our negative binomial regression model and interpret it. We have already seen how to fit the model, but there is something I want to show you about the reporting options that we do have. When we are fitting our model under reporting, we can either report coefficients, which are the default settings, like we've done here. We are reporting a model with coefficients, but also we can report incidence rate ratios. If I select it and click submit, we shall get a model that reports incidence rate ratios. But what I want us to appreciate is that the p-value, regardless of what you're reporting, will remain the same. For incidence rate ratios, age, we have 0.00, and for gender, we have 0.01. Even when we look at the model that is reporting coefficients, we still have the same p-values. So we are going to start by interpreting the model that has coefficients. In the output, you will see we have 200 observations, and we have the likelihood ratio chi-square with it is p-value here, which is statistically significant, indicating that by adding our variables into our model, there has been significant improvement in model fit compared to the null model or the model without any variables. We also have a pseudo R squared, which shows us the proportionate improvement in our model that could be attributed to the independent variables that we've put here in our model. However, this should be interpreted with caution because it is not directly interpreted like the R squared value that we have in linear regression. In the table here, we have our independent variables with their coefficients, standard error, the Z values with their corresponding p-values, and the 95% confidence intervals. I have prepared for us a PowerPoint to help us with the interpretation of these outputs. Before we make any interpretation, I want us to look at the formula for the negative binomial regression with the independent variables. This is how it is written out. It is the log of the expected value of the outcome that has a linear relationship with the independent variables. So whatever we are interpreting, these beta naught, beta 1, beta 2, and for whatever variables we have, They are interpreted in terms of a change in the natural log of the expected value of the outcome. So when we look at our constant, we shall start with the constant here, 0.83. This is the natural log of the expected value of the number of visits when all the predictors are equal to 0. And when we have a numerical variable like age here, that value is the difference in the natural log of expected value of outcome for a unit change in that variable when all other predictors are held constant and that variable does not interact with any other variable in the model. At this point, I expect you to have already checked for interaction in your model. We have a previous episode about checking for interaction under binary logistic regression. It will show you how you would check for interaction under this model because the principles are essentially the same. For a categorical variable like gender, you can see it is also statistically significant. So this value is the difference in the natural log of the expected value of outcome, in this case clinic visits, when subjects in one category are compared to subjects in another category. Here we are comparing when males are compared to females, and when the difference between the codes of categories is unity. The way you code your independent variable, there should be a unit difference. For example, 0 and 1 or 1 and 2. You shouldn't have groups coded as maybe 1 and 4. The difference in their coding would not be unit, and then mathematically the interpretations would be very different. There are other conditions that are included in the interpretation. For example, other predictors are held constant and that variable does not interact with any other variable in the model. Generally speaking, when you have a positive value for a numeric variable like age, it shows that for every unit increase in age, there is increased likelihood of having higher clinic visits. For a categorical variable, it means that that group compared to the other has a higher likelihood of visiting the hospital more than the one in the reference category. When you have a negative coefficient like the one we are seeing for males here, it shows reduced likelihood of visiting the doctor. That is also interpreted in comparison to the reference category, which are the females. Now let us look at a scenario where your model was reporting incident rate ratios. Still, we are going to borrow knowledge from how the negative binomial regression model is written out, which is the log of the expected value of your outcome, in our case clinic visits, is the one having a linear relationship with the predictor. So the constant, this one here, 2.294, is the natural log of the risk of the outcome when all predictors are equal to 0. For age, that is the difference in the natural log of risk of outcome for a unit change in that variable when all other predictors are held constant, and that variable does not interact with any other variable in the model. Just like we've seen, it is just this part of a difference in natural log of risk instead of natural log of expected value of outcome. Even for gender, we would say that is the difference in the natural log of risk of outcome when subjects in one category are compared to subjects in another category, when the difference between the codes of categories is unit and there is no interaction and all the other variables are held constant. Generally speaking, if you have an incident rate ratio of 1, it means that variable is not associated with the number of clinic visits. A value above 1 shows that that variable is associated with higher clinic visits, and less than 1 shows that variable is associated with lower clinic visits. If you found this video useful, consider liking and subscribing to the channel so that you don't miss out any of our episodes. In our next episode, we shall start on a series of videos under survival analysis, a type of analysis where our outcome is time to event. We shall cover the different models that are used in survival analysis and their interpretations. See you in the next episode.